Hi, everyone, and thanks for joining us for the Physiological fMRI Signals Educational course at OHBM 2023. I'm Mary Miedema, and I'm going to be giving a practical tutorial called Hands and Sensors On, a practical guide to acquiring your own physiological data and preparing it in BIDS format. So to begin, I have no financial interest to disclose, but I am a member of the PhysioPi community. We'll be talking more about that as we go forward. For today's tutorial, I want to demonstrate some very basic physiological data acquisition. I'll be focusing mainly on PPG and respiration. I'll show you some videos of our setup in the lab, and then talk about what that can even look like in the MRI environment. I'll very, very quickly touch on brain imaging data structures or BID specifications, just so that we can talk about how it makes sense to store and share your physiological data. And then I'll go through an interactive coding session, and I encourage you to follow along at home if you can. But if not, it will also be offered in person. And this will show how to use the Phys2Bids open source toolbox to convert your physiological acquisition files into BIDS format. So to start with, you've already heard quite a lot about the different ways to measure cardiac signals from the previous presenter, Dr. Molly Wright. I'm going to be talking about PPG specifically today, or photoplethysmography. For the main reason that it's easier to acquire in the scanner than ECG, it tends to be less susceptible to MR-related artifact. And the basic principle of this sensor is that we're using infrared light to measure changes in blood volume that are corresponding to the reflection of that light by hemoglobin. I'm going to be using some BioPack equipment in today's tutorial. I'll also briefly talk about scanner built-in available for PPG. I'll also spend time talking about respiratory effort measured with a respiration belt, again using BioPack equipment. There are a few different ways to measure respiratory effort, but most of them correspond to being sensitive to changes in abdominal or thoracic circumference that accompany breathing. So the particular belt that I'm going to demonstrate to you in just a minute has a stretch sensor, whereas the Siemens physiological monitoring unit that I'll touch on later is more sensitive to changes in pressure. Okay, we're going to go ahead and first talk about how to set up the respiration belt and look at some of those recordings in the lab environment. Later, I'll talk about how to do that in the MRI environment. So what I've got here is the respiratory belt. I'm going to go ahead and share my screen and show you the recording software I'm using, which is BioPack's Acknowledge. I'm going to go ahead and start the recording. The respiratory trace will appear at the top of the screen and the PPG later on at the bottom of the screen. For now, I just want to show you that when I pull on this respiratory belt, my signal increases. So again, we're just measuring that expansion of abdominal or thoracic circumference. So I'll go ahead and stop this for now. When you're setting up the belt, then you want to be really sensitive to changes in that circumference. So you're going to go ahead and ask your participant to take a deep breath. And I'm going to exaggerate this, but what you want to do is look at where the biggest changes are happening during their breathing. If they're breathing more from their upper chest, a breath might look something like this. So we have this change here, versus if they're breathing from lower in their abdomen, you'll see changes more around their diaphragm like this. Okay, that said, how someone is breathing can shift a lot depending on what you're asking them to do, and changes from going between sitting and standing, how nervous they are during a scan. But it's important to pay attention to and consider repositioning if you're not getting the signals that you want to see. Okay, I'm going to go ahead and put the belt on myself. So I'm just attaching the Velcro to both sides of the transducer. And you want to tighten it while the participant is fully exhaled. So we'll have a look and see what our signal seems to be doing. I'm going to start just by breathing normally. And I'm just going to change the scale so that the waveform is more clear to see. So you can see as I inhale, the signal increases. As I exhale, the signal decreases. When I start to talk, things go wonky. Okay, I will show you the difference between a shallow breath and a deeper breath. Again, I'm just going to change the scale. So here's a shallow breath. And a deep breath. So there can be quite a drastic difference in what you want to be sensitive to, depending on what you're asking your participants to do. Now, if we hadn't put the belt on quite correctly, let's say if we had put it on too tightly, I'd like to show you what that signal will look like. See, it went up, which makes sense with how our sensor works. And it seems like we're really losing a lot of our breathing cycle. We've got some clipping. It still is sensitive if I take a very deep breath. But it may not be as sensitive to all parts of the breathing cycle anymore. Likewise, if I loosen the belt too much, our signal decreases significantly. And it still changes depending on how I'm breathing. But again, we're no longer as sensitive to all parts of the breathing cycle. So what I would suggest doing is playing with tension until you're satisfied that you're recording all of the different kinds of breathing you're interested in your scan. Okay, I want to go ahead and show you the PPG now, which is arguably easier to place than the respiration belt. The nice thing is that the PPG is also much more convenient to adjust while you are scanning. It's harder to pull someone out of the scanner and change the belt, but it's not impossible to reach in, grab a hand and change the sensor. In general, you can choose a larger finger to position it on. You just want to be sensitive to changes in blood volume, so more blood vessels is a good thing. So here, I'm just going to attach it to my thumb, and I'm going to tighten the strap. And we'll go ahead and see what it looks like. Okay, so now we still have respiration on the top half of the screen, but on the bottom half of the screen, we have our PPG signal. I'll just change the scale so we can take a closer look at the waveform. And you can see one really, really, really nice. I'm going to pause it so we can appreciate one really nice waveform right down here. So right here, we have our systolic peak, then our diachronic notch, and a diastolic peak. And the peak to peak detection for this signal would be quite good. Now, let's take a look and see how that signal can change. So I've put the sensor on my right hand, and I'm actually moving that hand quite a bit right now. Here's me holding it quite still. We have a nice strong PPG signal. When I start to move that hand, I'm just moving my hand towards me now. It's not too bad. It's when I start to move my fingers that the signal really, really changes. So this is This is a measurement that's going to be very sensitive to how your participant is moving in the scanner. And depending on how much the participant moves, the sensor can shift a little bit on the finger. So I've just moved this sensor. It should return to some kind of baseline we can read, but the shape will have changed. And in fact, it looks like it's no longer in quite as nice contact with my skin. The amplitude is smaller. So this can be fixed by tightening the strap. You have to be careful not to cut off circulation entirely, or if a participant seems to be losing circulation, you can try another finger. So I've tightened the strap, and while the waveform doesn't look entirely the same, that's probably just a function of the new position of the sensor. I do also want to show what can happen if the sensor is too tight. So in this case, my signal is going down, and I start to also lose my sensitivity. And as I loosen the sensor, I start to be more sensitive to the waveform again. So you can see that as you set up the system, a really important step for both the respiration and the PPG is to take a look at your waveforms, see what they're doing, and see if you're happy with them. If not, probably tighten or loosen your sensors. Okay, so we've covered what it looks like to measure respiration and PPG in the lab. How do things change when we're at the hospital? They do get messier. You can probably tell that by these photos. So what I wanted to show you is our BioPack setup in the control room. And here you can see our main BioPack module. We have the same PPG and respiration modules that I was just using in the lab, but the sensors no longer connect directly. We have a set of filtered cables that attach to those modules and pass through the patch panel into the control room. That's one of the main differences. We need radio translucent MR compatible cables. However, the other main difference is that it becomes really, really important to have a way to measure your MRI scanner triggers. So we're doing that today with an additional channel called the UIM 100C your BioPack. Basically, you need to be recording alongside your physiological signals some marker of timing so that you should have a short, sharp pulse at the start of each TR. And we'll talk a little bit about that as we go. What things actually look like in the control room is you will get your participant set up on the scanning table as per usual, but you want to be really careful with how your cables are behaving in the scanning room. So what we like to do in our studies to avoid artifact and keep everyone safe is to have the cables coming out down through the bore very straight along the scanning table, and then we kind of spread them out in the scanning room and tape them down to avoid any loops or coils. It becomes important to be careful when you're moving the scanning table back and forth that you're not catching any wires. Now, having looked at the BioPack setup, it may seem simpler to use some scanner built-ins. We're scanning on a 3T Prisma scanner from Siemens, and they do have something they call the physiological monitoring unit, which are these two boxes I'm holding in the photo on the left. And these are basically Bluetooth equipped sensors that you can use. The one I'm holding on the right is a PPG. The one I'm holding on the left is both EKG and respiration. You can see the respiration belt itself. It's the large gray belt on the right. And these are fairly easy to set up. The setup is similar to the PPG and respiratory belt that I showed you before. Again, the belt goes around the abdomen, and the PPG sensor just slides right onto the finger. You can monitor these signals while you're acquiring data on the scanner. So on the bottom right, I'm showing two examples of what that looks like. And essentially the signals that you see while you're monitoring are also the signals you're going to record. The file format can be a little bit less intuitive to work with, but it is possible to export them for offline analysis. So in these two examples, you can see PPG data in the top row, and it's got little arrows detecting the peak-to-peak statistics. So it'll tell you things like your participant's heart rate in real time. And on the bottom, it has the respiratory waveform. And you can see in general, these curves are very smooth. And in fact, in the very bottom respiratory waveform, there's quite a bit of clipping. And this is the downside to using scanner built-ins. Although simple to set up, there isn't a good way to change your acquisition parameters or your filtering. And so it often means that the data you're getting is not highly informative about the shape of the waveform, and it's very easy to lose your respiratory waveform. So that's a significant downside of using a scanner built-in. One other thing I wanted to touch on is, do we see any MRI-specific artifacts? Often no, if we've set everything up correctly. You shouldn't see strong electromagnetic signals that seem time-locked to your sequence in your physiological data. However, that's not always true. So now I'm showing an example of physiological data we acquired during a scan. You can see I now have this top channel, which includes trigger pulses. So every time you see a spike, that's a new TR starting to be acquired by the scanner. Our respiratory waveform looks quite nice, but then on the bottom, the PPG waveform has some very clear mechanical issues. So this was something I was noticing for a number of our subjects. You can actually see as well, when I asked a subject to do a breath hold, you started to see strong PPG and even a little bit of that same artifact in the respiratory signal itself. So this is really undesirable. You can imagine it would be difficult to do peak detection with artifacts like this. Even if you can filter it out, it's better just not to have it. And what we found was that we could get rid of this artifact just by making sure everything was very tightly grounded when attaching it to the patch panel, and to make sure that there were absolutely no loops, even in the cables on the control room side. So that's just an example of a scanner artifact. It's at about 15 Hertz, so it's not very obvious what was causing it. But the important thing is to eliminate that as much as possible, just from a hardware perspective. Okay, so I'd like to finish here just with some takeaways for acquiring your own physiological data. What you really need to acquire physiological data in a scan setting are just MRI compatible sensors and accompanying trigger information. So you can do that with built-ins. You can also have a dedicated setup. And I really think it's worth taking time to explore this if you want to do any kind of sophisticated physiological data analysis. As well, really pay close attention to your sensor positioning, both at the start of the scan and throughout the scan. Monitor what's happening so that you can make adjustments to make sure that you're sensitive to the signal features you want to be sensitive to. And now I'm going to move into the second part of my tutorial, which is, once you've acquired your physiological data, what do you do with it? So for those of you who haven't heard of the brain imaging data structure or BIDS format before, what it is a set of standards that help people know how to format their data, what file types to use, what to call those files, and what folders to put them in, what information to share about those files will help other people know how to use them. And I've linked here some more information to give you a sense of the BIDS format. There's lots of great documentation on how to put things in BID format, how to work with BIDS format. You can get a general idea of, the messy files our labs might be acquiring on the left and the nice BIDS equivalents on the right. And what we're going to do is talk about how to do that for physiological data. There are two open source tools that I'm aware of that will let you do this. One is BIDS Physio. It supports a number of different formats, and I believe is fairly up to date, though I myself haven't used it. The second one is Phys2Bids, and that's a toolbox developed under the umbrella of the PhysioPy community, which I am part of. And so for today's tutorial, I'm going to be walking through how to use Phys2Bids. It's really actively under development in that there are well-supported versions and a lot of documentation out there, but if it's not doing something that you'd like it to do, um, there's a lot of potential to either ask for that to be developed or to get involved in development yourself. So if you're interested, I encourage you to reach out to us. We currently support a number of different file formats, including acknowledged files, lab chart, um, SPIC2 formats, and GE scanner built-ins. You can check out our GitHub repo and documentation for more information. So I'm going to show you how to use this tool in Python 3. The content may change a little bit between this online recorded version of the tutorial and the version we're offering at the in-person course. You can always refer to the online Phys2Vids documentation for updates. I am recording this using Windows 11 in July 2023. If you'd like to try this out for yourself, you can download a Docker container with a basic installation of Phys2Vids, just at Miedema /Phys2Vids base. You can also download all of the individual files that I'm using in today's tutorial using the following links. So with that, we'll get started. Okay, we're going to go ahead and get started with our Phys2Vids tutorial. What I'm doing is running from inside VS Code on Windows 11 a Docker image that is essentially going to let me run Python within an Ubuntu container. So you don't need to worry about this part too much. Essentially, as long as you have a command line of your preference and Python installed, you should be able to do what I'm doing now. But I'm going to go ahead and install Phys2Vids, just using pip, and I'm going to specify the argument in square brackets that you see, ACQ or ACK. That's to specify that I want Phys2Vids to be able to handle acknowledged files. So it'll install a few other packages that allow us to do that. And now that everything is installed, I'm going to go ahead and check that Phys2Vids will be able to run successfully. I'm just going to type in Phys2Vids with the -H, or you could run -help as a flag here. And you see that we get back lots of information about how we're able to use the command line interface for Phys2Vids. Okay. Next, I'm going to go ahead and download a number of files for our tutorial to run on. You'll have the links for these separately if you attend the in-person course, or they'll be posted on one of the slides. And these will also just take a minute to download to our workspace. One of these is an acknowledged file like the kind we recorded earlier in today's tutorial, while another one is actually a lab chart recording, so a different format. So we can go ahead and check that we have our 3 files, and we're good to go with the rest of the tutorial. Okay, we're going to go ahead and now use Phys2Vids to check out some information about our first file. And we do this just by specifying the input file. Here I'm using the file called samefreq_multiscan.txt, and I'm using the info flag. So it's just going to read things in and tell me about that scan. So here it tells me that that scan contains some MRI trigger information, as well as some CO2 gas traces, both sampled at 100 Hertz. We can do the same thing, but for our acknowledged file, and we'll get a different set of information. You can see that in the multi-freq acquisition file, we instead have respiration data, pulse data, trigger data, PPG data, CO2 data, and O2 data, and as the file name indicates, some of these are sampled at different frequencies. You can also see, and you can see this more clearly if I now ls and show you the code folder, that we have a new folder created just by checking the info of each of these files. And in that, we have two new figures, each with the same name as our input files. So we'll go ahead and take a look at those. Okay, so we can now go ahead and have a look at these. First, we'll check out our same frequency multi-scan. And here, just as we saw in our info, we have two channels. The first is MR triggers, and in fact, we have two sets of MRI triggers. So we've recorded two separate functional sessions here. And then on the bottom, we have CO2 traces, and you can see actually some breath holds at the start of this recording. If we check out now instead, the multi-frequency file, the plot it created shows us all our different kinds of data as well. Our breathing traces look familiar. We have our MRI triggers in scan 03, our PPG, and our gas recordings don't actually look very nice. It's possible someone forgot to connect them. So we'll talk about what to do with this later, but this is just a simple quality control inspection you can do with Phys2Bids to make sure all of your data is being read in properly and everything makes sense. Okay, so now that we've taken a look at that first file where we had CO2 traces and MR scanner traces, we're going to run Phys2Bids again with that as our input. However, now we're going to specify the number of time points in each of those two sessions that we saw. So that's here, that's this NTP argument, and I know exactly how many scan volumes we collected during each of those, as well as the TR. So I'll specify both those things, and we can see that Phys2Bids gives us a lot of outputs. Oops. So what it's doing right now is reading in that file again. It checks that we have the trigger in the CO2 channel, and then it starts breaking that file into two separate plots. It counts the trigger points in channel 1, and first it finds, just like we specified, the right number of time points, which would be 534. Then it's going to split the endpoint file, and it finds those second set of 513 time points. So we'll go ahead and have a look at the outputs this time. In our code conversion folder, we have the same figure as before, which shows us the entire read-in data. Sorry, let me just switch my screen. Okay, so as you can see before, in that folder, we do have the same figure as before, which shows us the entirety of the data we were reading in. However, now we see that we have this same data split into pieces. So if we look at same frequency underscore multiscan underscore 01, what it's going to show us is essentially where it took that first slice of data for those first 534 volumes. And you can see here that there's a little bit of a buffer because we want some information about physiological signals just before our first volume and just after at the end. Likewise, we can see where it trimmed the second half of our data. And so what we see is that it's started to export some text documents. However, just because it's broken our data into pieces doesn't mean it's in BIDS format yet. So the last thing we're going to do with this particular file is actually go ahead and put everything in BIDS format. So what we need to actually convert everything into BIDS format is one more file. We're going to download it right now. And this is a heuristic file. It's a Python type file. And it will allow us to specify some of the information we want the BIDS file structure to look like. So we'll go ahead and have a look at this file. Most of it is populated for you as a template. And what we see is that it's mostly a set of matching statements. And at the very end of the file is the part that you might edit. So here, in this if section, what we have is essentially we're searching for the file name that we're loading in, and we're able to label, as we split the file, which tasks are which. So in this particular case, we want to specify that the first part of that file contains our breath holds and a resting state scan, and then the second set of volumes in that file correspond to a cue deep breathing task. We can also include some other information that will be written into the BIDS headers. Okay, now we're ready for the last step, which is to actually use Phys to BIDS. And once again, with our same input file, we're going to go ahead, importing the same timing information as last time, the number of time points, the TR. Now we're going to include a subject and session number. And lastly, we'll link to the heuristic file. And we'll go ahead and put everything in BIDS format. It's finding the correct number of triggers, and we'll have a look at the output. You can see we now have a lot of information in this same folder. Two new things are the participants.tsv header and the README, as well as the dataset description. And these are all things that BIDS would traditionally have in its highest level folder. However, we can go ahead and look at the subject folder to see specifically what our outputs look like. Here, it's put our physiological files into subject 1's folder for session 1, just like we specified. And because it's neuroimaging data and most compatible, therefore, with fMRI as a toolbox, it's automatically assumed that everything should be in the functional folder. And so we can see here, it split things into our two separate tasks. And so we can go ahead and use this subject 1 folder as our physiological folder in BIDS format. Okay, so returning to our multi-frequency data, we can see that this is what it looks like. We have our respiration data, pulse data that's been recorded at a different frequency on a custom channel, PPG data, our trigger channel, and these last two channels don't look very nice at all. It's possible that they weren't even connected during the scan. So what we'd like to do now is convert this data to BIDS format. Because we're sampling at different frequencies, it's going to be a little bit more complicated, but we'll go through it now. We can use, in fact, the same heuristic file. Because of the flexible format of the file, all we really need to do is specify that we might be looking for a different file name and a different task. So using Phys to BIDS once again, this time with the multi-frequency file, we specify the number of time points, the TR, the subject number. We can use a different one to differentiate from our other BIDS conversion, the heuristic file, and now we can also use the channel select argument to drop the last two channels. So here we're specifying only the channels we want to keep. We go ahead and run. And you'll notice here that BIDS is writing to the same top level files that it created in its previous call with the same frequency multi-scan data. So the participants TSV file has been updated. So we can take a look. We still have our participants TSD file and our dataset description. You can see now we have subjects 1 and 2. And now if we actually look at our subject 2 folder, once again, in our functional folder, we have our files. And here they've been separated not by their scan numbers, they're both corresponding to some unknown task, but by their scanning frequency. And so that's how we can use phys2bits to generate folders that are in bits compatible format for our physiological data. I hope this has been helpful. I know there's still a lot to cover when it comes to getting started on acquiring your own physiological data, but I'm happy to talk more. If you have any questions, please reach out to me. I'd like to thank the PhysioPy community who's been really helpful in my own learning, my lab mates at the Biosignals and System Analysis Lab at McGill, my supervisor, Dr. Giorgio Smitzes, and the Montreal General Hospital MRI Research Platform for their help as well. So thank you very much.